The squeeze theorem allows us to compute limits provided that we can set them up in a certain way. So squeeze theorem, let f of x be less than or equal to g of x be less than or equal to h of x. So we have three functions. One of them is less than or equal to the next, and that's less than or equal to the next. So they're kind of in a row. But they could be equal. Let L be a real number. Okay? If the limit of f of x equals the limit of h of x, and they happen to equal the real number L, then the limit in the middle is also L. So what this says is if you have three stacked functions and the top and the bottom ones do something, then the one in the middle also must do that. And we'll do a couple examples where we use this. And to use this, we need to first find a setup. And some functions, well, a class of functions which allows us to find a setup like that are the trig functions, sine and cosine. So let's show that the limit of x cosine of x is 0. Now, you might think that you can show this right now through a direct substitution. But we actually can't, even though a direct substitution would be, what, 0 times 1. We don't have, yet, a direct substitution rule for trig functions. The algebraic limit laws don't apply to trig functions. But what we can do is use the squeeze theorem. So observe. Well, we want to think about x cosine x, but we know cosine x itself is always between 1 and negative 1. It's always between 1 and negative 1. Just look at the graph of cosine x. It's always between 1 and negative 1. Well, that's great. We have an observation about cosine, but we care about x cosine. Well, how can we resolve that? Well, let's throw an x on it. What happens if we throw an x on it? Well, it changes the equation. If we throw an x on this, we have to throw an x on everything. Well, that's great. Now, we want the limit as x approaches 0 here. Well, I'm going to introduce some shorthand notation. We want the limit as x approaches 0 here. Well, if the limit as x approaches 0 here equals the limit as x approaches 0 here, then the limit in the inside is 0. So let's take the limit as x approaches 0 on both sides of this inequality. And I'm going to do that with a large arrow. This large arrow, we will assume that we're talking about what happens as x goes to 0, and since that's what this is saying. If it said limit as x approaches 12, we would assume as x approaches 12. But here, we're letting x approach 0 because that's what we want to do. As x approaches 0, what does x do? Well, that side approaches 0 by a direct substitution, algebraic limit law. What about this other side? As x approaches 0, negative x approaches 0. So we have that the function in consideration is squeezed between two things which have a limit of 0, which allows us to conclude that the limit is 0. So I would normally write this under here, but I drew those arrows a little large, so I'm just going to write it over here. So I'll say, therefore, limit as x approaches 0 of x cosine x equals 0 by squeeze theorem. So we used cosine to find two functions that we could squeeze our original function between. Let's do another. Let's do one where we'll never be able to do a direct substitution. These, well, by the end of another video this week, we'll be able to do a direct substitution for trig. But this next example, we can't do a direct substitution, ever. Example. Evaluate the limit. Now notice here I'm not saying by squeeze theorem. I'm also not stating it like this where I told you the limit. Here we're just evaluating the limit, and we're going to see what squeeze theorem throws out. If you have trig and you can't do a direct substitution, that's in Calc 1 a very large squeeze theorem hint. So let's evaluate this limit. You can't do a direct substitution because inside here you'd get 1 over 0. Even though it looks like 0 times something, 0 times infinity, for example, isn't always 0 or infinity. But what we can do here is use sine to our advantage. Remember, sine of x, maybe I should draw a y-axis. That looks terrible. Sine of x, remember, just like cosine, wow, that's terrible. Yeah, good enough, is between 1 and negative 1. So we can do that here. So observe. Negative 1 is less than or equal to, we have sine of 1 over x squared. That's okay. I mean, 1 over x squared is still going to be a number most of the time. It's not a number at 0, but we don't care what happens at 0. We care what happens close to 0. So we can still make this observation about sine of 1 over x squared. Well, now let's make this more interesting, I guess. I'm going to just throw a cube on that, I hope. Well, that shouldn't cause you to have to erase it. Because we had an x over here, and why would I do the same thing? I mean, I have it right here in my notes, both with x. I probably should have caught that. Where were we? So we have this observation. Well, that's not the function we want. We want this function. Well, okay. We can force that function into existence by throwing an x cubed on that. Well, I mean, there's a cost to throwing an x cubed on that. You can't just throw an x cubed on something and not throw it on everything else, unless you want to lose credit. So we put an x cubed on everything. Well, we again want the limit as x approaches 0. We have the function we want between these. So if the limit on this side is the same as the limit on this side, well, then we can conclude using squeeze theorem what this limit is. So what is the limit on this side? Well, as x approaches 0, negative x cubed through a substitution, direct substitution, or limit laws. Limit laws, what, 7 and I guess 4, 7, 4, and 2. The limit here is 0. Direct substitution. Limit as x approaches 0, because that's the one we want, of x cubed is also 0. Well, now we just have to reach our conclusion. The limits on both sides, of that inequality are 0. Therefore, limit as x approaches 0 of x cubed sine 1 over x squared equals 0, and we'll say by squeeze theorem. Sometimes when you're writing squeeze theorem, you just scribble the words like that. And as long as you can see like an SQ and a Z, it's pretty clear what that means. So these first two, we applied squeeze theorem by setting up an equation which was really the result of a graph. And with sines and cosines, that's quite common. Another way to set up a squeeze theorem inequality is geometrically. So let's do one. We'll do one, and then I'll post another. I hope I remember to post this one. I'll post another for you to look at. I won't ask about it because it's pretty complicated, but I will post it. It's definitely worth looking at the geometry. Theorem. We're going to prove limit as x approaches 0 of sine of x equals 0. We're going to prove it using squeeze theorem. We're not going to prove it with a direct substitution. That will be later today. We're going to prove this, and to start this, I'm going to draw a picture using the unit circle. I'm just going to look at the first quadrant because that's all we need. That's good. I have two similar pictures, so I thought I looked at the wrong one. So this is an arc of the unit circle. So the radius is 1, which will be useful. Okay, we have this arc of the unit circle, and we have some labels. This vertical line is sine of theta, because the hypotenuse is 1. The radius is 1, I should say, or hypotenuse. What is this length? Well, remember, this is the unit circle. That length is defined to be this angle in radians. And this angle is in radians, because it's always in radians. So this length is the angle theta. It's the distance theta in radians. Well, this is actually all we need. Sine theta, notice sine theta, that is we're looking in the first quadrant here, this is always a positive vertical distance. So we'll say from the diagram, it's always positive. It's always larger than 0. Sine of theta is. Sine of theta is this vertical line, this vertical distance. This vertical distance is less than this arc distance, which is given by theta. Well, this is actually all we need. Maybe I should use x's. I actually remember last semester I did the same exact thing with x's up here and thetas here, and I left it. I'm going to leave it because this is from the diagram. In general, we'll be dealing with x a lot more than thetas. But right here, we have 0 is less than or equal to sine of theta, less than or equal to that curved length theta. Well, we want to know what happens as the variable goes to 0. Well, this goes to 0 because it's just 0. 0 doesn't change as theta goes to 0. This is theta. As theta goes to 0, theta goes to 0. So therefore, limit, we have the limit on this side is 0, the limit on that side is 0. As theta approaches 0, of sine of theta equals 0 by squeeze theorem. And the theorem above follows by letting theta equal x. So right here, now we have that the limit of sine of theta as theta goes to 0 is 0. We could just make a couple of remarks. I mean, these are also theorems technically, but I'm just going to call them remarks. Limit as x goes to 0 of cosine x, well, we'd like it to be 1 through a direct substitution, but we don't have direct substitution for trig functions and limits yet. But what we do have is a relation between sine and cosine. Sine squared plus cosine squared is 1, so cosine is root 1 minus sine squared. And we have the limit laws. The limit laws, so I'll say equals by limit laws, let's see, we have a power, so that's by 7. We have a sum, so that's by 3. We have a limit as x approaches 0 of 1, so that's by rule 1. So by limit laws 7, 3, 1, and that theorem, so I'll say and previous theorem, this all equals, let's do it like this, equals root 1 minus, how should I write this? Equals root 1 minus limit as x approaches 0 of sine of x. Okay, I guess I didn't apply the previous theorem. By using those limit laws, this equals that. And by using that theorem, we get root 1 minus 0. We need a square. We technically applied rule 7 twice to get it inside the square root and then to get it inside the root. That limit is 1 because this limit is 0. You can think of this as a direct substitution by the end of continuity. But we have now that the limit as x approaches 0 of cosine of x is 1, as expected. We can also now find the limit as x approaches 0 of tangent of x. So let's just do that up here. Limit as x approaches 0, so this is a continuation of this remark. So this is remark bullet point 1, remark bullet point 2. Tangent x as x approaches 0, well, tangent is sine over cosine. Notice, I didn't get rid of the limit until we actually took the limits. Can't get rid of the limit until you take the limit, unless you want to be wrong. Limit as x approaches 0 of tangent x is the same as the limit as x approaches 0 of sine x over cosine x, which equals, by limit rule 6, the quotient one, limit as x approaches 0 of sine of x over limit as x approaches 0 of cosine x. And by the last two results, this equals 0 over 1, which is 0 as expected through a substitution argument. So the squeeze theorem, I mean, you could, I'm not going to ask a diagram squeeze theorem. If I ask a squeeze theorem, it would be more likely to be like the second example we did with sine of 1 over x squared. But definitely look through the squeeze theorem page posted on Canvas. It'll be in week 1, it'll be called squeeze theorem or something.